The brain is nature's greatest work of art and science's greatest fascination. Despite the fact that we use it to think and process everything around us, we understand quite little about how exactly it works. What we do know is that the brain is made up of special cells called neurons, and we know that these neurons connect to one another in a large web all around our brains. And we know that through this web of neurons, our brain can take in certain information as input and set off certain reactions as output. But as for what exactly occurs between the input and the output through the neurons, we may never know considering the complexity and sheer number of connections and pathways. But that has not stopped scientists from trying to create machines that mimic the neuron model of learning. These scientists call these learning machines, not so originally, neural networks. Networks of neurons. One of the most recognizable applications of neural nets is for image recognition. Look at your Snapchat filters and the way they follow your face. Snapchat actually trained neural networks to create the algorithm that recognizes patterns on your face and places images on them. That's right, Snapchat trains their algorithms. And that's not just something they do, everyone trains neural networks. That's the beauty of them. Like a brain, they can adjust and learn from their mistakes and get better through use. And of course, like any reasonable person, you might ask, how do they work? See, artificial neural networks are a little more organized than those in the brain. For example, if we are Snapchat and we want some image recognition algorithm that can detect whether we are looking at a face, we will probably have input neurons that each correspond to a pixel and encode its brightness on a scale of 0 to 1. We will probably also have neurons that correspond to the color of each pixel. So, in short, a lot of input neurons. Then we look at our output. Let's keep it simple and say we have one output neuron for now that will hold a value from 0 to 1 that encodes how sure it is that the input picture has a face. We could have other outputs that might encode the location of the face, but for now let's keep it that simple. And then there are these rows of neurons in between. These are the hidden layers which do the heavy lifting of the algorithm. And these layers essentially work to break down the problem into smaller and more manageable parts. But before diving into how that works, we must understand how exactly these neurons communicate. Let's look at a neuron from the hidden layer taking information from the input layer. Let's say this specific neuron is going to have a strength from 0 to 1 that is supposed to dictate how certain it is that some very small element of a face is somewhere on the screen. For example, the pupil of an eye. What it's going to look for is a very dark area surrounded by some solid colored area, the iris, right? Therefore, it will have stronger connection to the areas that it thinks will have a pupil. Mathematically, these connections are represented as a strength factor. Each neuron adds up all the previous neurons with these strength factors, and it proceeds to add a bias factor that changes how active the neuron is compared to other neurons. These bias factors can differ between neurons and change how much power a single neuron's value can have in the grand scheme. And after all this addition and subtraction, the value the neuron has can be pretty big or it can be negative. Therefore, it proceeds to use a function that brings it back into the range between 1 and 0. Now, this neuron very roughly has an estimate for how sure it is of seeing a very small facial part. But see, we can have lots of neurons in this level put towards encoding how sure it is of seeing small, specific facial parts. In the next hidden layer, we can proceed to combine these values to find how sure we are of seeing even larger facial parts. For example, we can combine the values for pupil and eyelid and eyelash to get the value for an eye, and we can continue with other parts. And by the end, we can combine the confidence we have of seeing everything, eyes, nose, mouth, ears, chin, cheeks, to come up with a final value of how sure it is of seeing a face. And then we get this value. But what if the value's wrong? I mean, there were lots of weights and biases, and whatever guesses we had for them were probably flawed in the beginning. We might have a completely terrible algorithm. And that's fine. Machine learning algorithms are supposed to start off weak. What makes machine learning special is the fact that these algorithms can learn. Now, as for how they learn, there are quite a few steps. The first step involves gauging how terrible the algorithm is. The function for finding this out is known as the cost function. Let's say our first trial, we show this algorithm a face, and it spits out a really low number because its weights and biases suck and it doesn't really work. What we do is take the square of the difference of what we want and what we get. The more correct that value is, the smaller this cost will be, and vice versa. We then do this with a ton of testing data and average out the cost numbers that we get. So now we have this cost function. The inputs to this cost function are the weights and biases, and the output in turn is the cost. So if we wanted, we can imagine it as some 1,000-dimensional plane in which we have all the input dimensions and one output dimension. And in that huge graph of so many possibilities, we have one point: our average cost over a lot of testing data. Now, we don't know what this function totally looks like, with all the possibilities that can arise from changing the weights and biases. What we can get from this graph, however, is a vector, a shift we can make to our inputs. And what this vector does is point us towards a local minimum in the graph. Of course, it's impossible to really imagine that with thousands of input directions, so let's imagine it in a graph with one input and one output. If our function is here on the graph, we can compute a vector that will point us down towards the local minimum. And if you think about it, it's a matter of slope. We want our slope to approach 0. And if you think about it, that's calculus.
And since we have a billion variables, it's multivariable calculus.
So computing that special vector requires multivariable calculus, and I won't attempt to explain that. This whole process is known as gradient descent. In other words, we are trying to descend a slope in the cost function to reach some local minimum by calculating this gradient vector. Anyways, now that we have this huge multivariable vector containing the weights and biases that we want to change, we can then apply it to our vector of old weights and biases. And then we run our new algorithm with the new weights and biases into the cost function, get a new vector, and continue the cycle until our cost is as minimized as possible, until it reached the valley in the cost function. And that's basically what it is. We run the neural net, get a cost, and proceed to descend the cost function little by little in order to train the algorithm. It's pretty complicated, not gonna lie. But to be fair, so are our brains. In any case, I think it's reassuring that the function is so complicated, because we know at heart that some simple function can never replicate the learning that goes on in our brains. And neural nets are just one type of machine learning. There are many different types being developed for a wide variety of things, and they're pointing to a future full of intelligent robots. Of course, as of now, almost all artificial intelligence we have is narrow. It's really good at a single task, like image recognition, or ad recommendations, or playing chess. We have yet to make a completely all-purpose AI brain that works similarly to the human mind. But what with all the rapid progress that machine learning has made in the 50 years since it was developed, I think it will happen soon enough. And that comes with a whole host of problems we can discuss in a future video. But for now, I hope I helped you grasp how basic neural nets function. Thanks for watching.